that is still open is to decide whether the set of volume polynomials over K depends on K or not. So in all known cases in degree 2 or in 2 variables, it doesn't because they were simply the set of all Lorentzian polynomials. But in general, you know that the set of volume polynomials and Lorentzian polynomials differ, but there's one for every field K or characteristic of K, and you don't know whether this set actually changes or not changes.
I apologize. Where did it? And you go.
If we can go to the full screen mode, I can navigate. Yeah, so in the meantime, I'll just tell you how to show that some Lorentzian polynomial is not a volume polynomial over K or any K. So what you have to find is a universal inequality between the intersection numbers of map divisors that's valid over any projective variable, no matter characteristic, no matter singularity, no matter what. And one thing you can do is to use an inequality discovered by Brian Lehman and Jian Xiao some time ago, first in characteristic 0. The idea was to pretend that the field K is the complex numbers and pass it to resolution of singularities, and you try to do some analysis. So in particular, you apply the solution to the multi-pair equations using Gauss' theorem to, in a sense, uniformize one of the classes. And then you can use this tool to transfer some of the known inequalities for positive definite matrices, which is a local version of the inequality valid for every point in the Keller manifold. Transfer to it to a global inequality between intersection numbers, their intervals. It's not so clear which kind of determinantal inequalities for positive definite matrices can be transferred using Gauss' theorem or variance theorem. But you can transfer some of them, and it can be used to show that, for example, this Lorentzian polynomial is not a volume polynomial over C. And then there was another follow-up work, which shows that using open-flow bodies and restricted volumes and so on, you can do something very similar over characteristic. Now I cannot move. Yeah.
Just click here.
Yeah. Okay. Great. Okay. So this is the sort of a main combinatorial definition for today, again introduced by Whitney. And in a sense, this was the whole point for Whitney to introduce the notion of matroids. So E is a finite set, and M is a matroid on E. The dual of a matroid M on E is the matroid M check on E, whose bases are exactly the complements of the basis of M in E. And that the fact that this is a matroid is clear because symmetric exchange axiom is symmetric. Okay, this was the main example for Whitney. So if you have a planar graph, you draw it on a plane in some way, anyway, and you draw the dual planar graph, OG check, and notice that their spanning trees of G and G check are in bijection to each other by taking complements. So the matroid of G is the dual of the matroid of G check. And Whitney's theorem is that a graph is planar if and only if its dual is also a graphic matroid. So this picture tells you one direction, and his theorem is that actually planar graphs are the only cases where this happens. So some of us were in Stefan's lecture yesterday, where we have learned the importance of being graphic or co-graphic, dual graphic, in the context of cycles on abelian varieties. So we now have a geometric way of understanding what this matroid geometry is in a much, much wider context. It is simply the geometry between Grassmannians. So there's an isomorphism between Grassmannian Dn and Grassmannian n minus d, which sends W to W perp. And this isomorphism has a very pleasant description in terms of Plücker coordinates. It's literally the same Plücker coordinates. You just have to replace the legend set by the complement. And therefore, this isomorphism exists not only over a field, but for any tract. So if you plug in this final tract K, the cross-layer hyperfield, you will see that you're exactly getting with this matroid geometry. And yesterday I told you that the space of log concave polynomials is basically a Grassmannian or thin sugar cell in it of a Grassmannian over the triangular hyperfield T1. And if I plug in T1 over there, I get isomorphism here and there. So it is very natural to ask the following two questions. What happens to log concave polynomials under this geometry? It's just simply an operation of replacing every monomial by a complementary monomial. And what happens to volume polynomials under this geometry? Those two questions are the main questions for today. Okay. So I'm going to introduce one very classical theorem definition that goes back to the classical period of abstract algebraic geometry. So Steins and Van der Waerden and McLean were thinking of transcendence degree of a field extension, and they wanted to prove that any two transcendental bases of a field extension have the same cardinality. And they have observed, in essence, that the resulting algebraic independence defines a matroid. It satisfies the exchange axiom. So let F be a field extension of K, E be a finite subset of the extended field F, and then you say that the collection of transcendence bases of F over K contained in E is a matroid on E, and any matroid that arises in this way, you call it algebraic matroid over K. And here, the realization problem is to decide, given a matroid, decide whether or not it is an algebraic matroid over K for a given K. I'm not going to read the rest of the thing, but in case you're wondering, I'm just pointing out that the corresponding realization problem is equally natural in the context, more general context of polymatroids. You don't choose elements of the extended field. You choose a bunch of intermediate fields and try to measure the transcendence degree of all the possible compositums. And then that's the rank function of your matroid. You can equally explicitly describe the corresponding generalized permutohedra. Same information. A long-standing open problem, sometimes attributed to McLean, is the following question. If M is an algebraic matroid over K, is the dual matroid algebraic matroid over K? This is still open. We happen to know the answer is yes when K has characteristics U. Our contribution is the following reformulation. The theorem is that the two conditions are equivalent for any collection J and any field K. The first condition is that J is a matroid that is algebraic over K. And the second condition is that there is a realizable volume polynomial over K whose support is J. So this algebraic matroid question is exactly the question about the existence of a projective variety and bunch of semi-ample divisors on. And using this perspective, you can recover and sometimes strengthen some of the classical results in algebraic matroid theory. For example, this corollary is rather natural to show in our context, which is that the matroid is algebraic over some field of characteristic P if and only if it is algebraic over all fields of characteristic P. This simply follows from my previous assertion that the set of realizable volume polynomial only depends on the characteristic. But if you try to show this directly in terms of field extensions and elements in it, it's very awkward to work with. Okay, let's recall that the space of Lorentzian or log concave polynomials is homeomorphic to the thin Schubert cell GRJ of triangular T1. I have told you that the GLJ over T1 is isomorphic to GLJ check of T1, the matroid duality. And therefore, you can ask, what is the relationship between log concave polynomials supported on J and log concave polynomials supported on J check? Here, I should emphasize that the main result from yesterday was that Lj and the Grassmannian over T1 are naturally homeomorphic to each other. But I didn't claim that they are equal to each other. If they were equal to each other, then the answer to the question would be trivial. But the reality is more interesting. Let me just make a short remark that when J is a polymatroid, the dual is defined only up to translation, because this duality operation refers to taking complement of a set inside a fixed universal set. But if you have a multi-set, it's not so clear what should be your ambient set. But the point is that it doesn't matter which ambient set you choose. Okay, here's the example. Look at the quadratic form with those entries, 4 and 1s, and you can check that this is a point inside Grassmannian 2,5 over T2. If you think of three-term Plücker relations, you see that there are 4 degenerate triangles and 1 equilateral triangle, so it satisfies all the Plücker relations. And therefore, its dual is Grassmannian 3,5. And it's a cubic form in 5 variables. But then you can check that this obvious dual is a Lorentzian polynomial, but the original quadratic form or the matrix is not Lorentzian. And this is to be expected. If you take the dual, you get a cubic form. How do you check that that's Lorentzian? You take derivative in all possible ways, 5 ways. You check that these are Lorentzian. And this corresponds to the size of the 4x4 principal minors of this matrix. But the saying that the original 5x5 is Lorentzian also involves the determinant of the full 5x5 thing. And it's the sign of the 5x5 is not implied by the correct sign of the 4x4s. Okay, so let me set up now the notations to formulate the main results relating to matroid duality. Okay, so I'm going to work with 2 polynomial rings, and just realizing that I need to do so was a big hint for formulating the statements in the right way. So in characteristic 0, people rarely think about this. But polynomial ring is like isomorphic to its dual. It's like Hope algebra. So on one side, you have a polynomial ring with some variables that I call partial. And on the other side, you have a polynomial ring in variables x. And I don't want to worry about the number of variables. So let me just take the limit and go to infinity. And I'm going to write monomials in partial by partial to the alpha and x by x to the alpha, bracket alpha, where the x to the bracket alpha refers to the normalized monomial, where you have to divide by factorials. This is the basis of the divided power algebra. And then you notice that there is a pairing between the two, or rather, there is one is a module over the other. You can act simply by differentiate. So partial alpha acts on x to the bracket beta by spitting out x to the bracket beta minus alpha if alpha is at most beta component-wise, if otherwise 0. So this is a usual differentiation, but let me refer to it as the cap product. I'm imagining on one side I have something like homology, and on the other side I have something like homology. If you don't like this, you don't have to do this, but this is a nice way to memorize how the formulation goes. Okay. And then I'm going to need a set in which I can take the complements of monomials. So I'm going to fix a vector mu, and I'm going to write by all partial at most mu be the span of all monomials partial alpha for alpha at most mu, and there will be the corresponding space for Rx side as well. And then there is an isomorphism of vector space between the two spaces where the map is simply given by the module structure, the differentiation. But in reality, this is just taking complement of monomials. The only new thing is that I don't want to use the same variables for this monomial and the complementary monomial. There will be the two sets of variables, and it will be useful to distinguish these two. And sometimes I'm going to refer to this obvious isomorphism as Poincare duality. And Poincare duality happens to be related to matroid duality. Okay. And here is a definition. So for example, if you have a polynomial in one of these spaces, the first space, and we say that G is a dually Lorentzian polynomial if the corresponding polynomial on the X side is a Lorentzian polynomial. So I'm just using the obvious isomorphism to transfer structures here. And it turns out that this condition only depends on the polynomial and not on the mu, the ambient set in which you're taking complement. And my collaborator Hendrik Suss and his collaborators, Julius Ross and Thomas Wanderer, formulated the following wonderful statement. They realized that the following two statements are equivalent. The first is that G is a dually Lorentzian polynomial in the sense of the previous slide. You simply take the complement of every monomial and hope that it's a Lorentzian polynomial. And the second is that for any Lorentzian polynomial f, if you act on that polynomial on x by G, which is a polynomial on partial, by differentiation, that is a Lorentzian polynomial. These two are equivalent. That's the theorem. So we can play the same game for volume polynomials. The definition is that if you have a polynomial on the partial side for a field K, you say that G is a realizable co-volume polynomial over K if this complement is a realizable volume polynomial over K. And the co-volume polynomial over K is the limit of realizable co-volume polynomials over K. So exactly the same kind of definition. And the theorem also have the same shape. The following conditions are equivalent for any polynomial G in the partial side. The first is that G is a realizable co-volume polynomial over K. So its complement or dual is a realizable volume polynomial over K. And the second is that for any realizable volume polynomial f over K, G partial acted on f of x is a realizable volume polynomial over K. So in this sense, co-volume polynomials and volume polynomials are dual to each other. And this statement, you can delete realizable from everywhere. That's a weaker statement. And here is another version of the main theorem, which looks basically the same, but the mathematical content is surprisingly different. So here, the assertion is that two statements are equivalent. First, f is a realizable volume polynomial over K. Second, for any realizable co-volume polynomial over K, if you act on it by the given f, then you get a realizable co-volume polynomial over K. So it's like a mirror statement. Let me convince you that these two statements are very different by looking at the following corollaries. So the first corollary says that if G1 and G2 are realizable co-volume polynomials over K, then G1 times G2 is a realizable co-volume polynomial over K. Because I can think of them as operators that preserves some class. I don't care what class. That class happens to be realizable volume polynomials, but If you have operators that preserve something, then you can take the product and it still is there. That's one corollary. That's the corollary of the first statement. The mirror statement is that if you have two realizable volume polynomials over K, then their product is a realizable volume polynomial over K. But the second corollary has a very straightforward direct proof. Suppose F1 is realized by Y1 and some left divisors, and F2 is by Y2 and maybe some semi-helpful divisors. You take the product of the two varieties, you pull back the left divisors from each vectors, and you take the sum and you compute the new polynomial, you get this thing. That's the obvious proof. What can you do to prove the first corollary? This feels very different, and I think it is very different. Okay. So there are some applications of this. What's this? New inequalities in Grun-Minkowski theory of mixed volumes of convex bodies. And typical application, I imagine, can go something like this. Suppose you have a volume polynomial of convex bodies Fc. And then maybe you know some famous inequalities in convex geometry. I don't really care at this point what they are. Just choose one of your favorite. And then the claim is that then for any covolume polynomial G, you can apply G to your F and get a new realizable volume polynomial. And apply your inequality to the new thing, which then the new thing, the coefficients are entirely determined by the coefficients of the original thing, and apply the inequality to the new thing, and then you have a new inequality. So for example, we know from geometry that all sure polynomials are covolume polynomials, like x1 squared plus x1 x2 plus x2 squared is covolume polynomial. You act on by that, and you have a very explicit linear combination, and you can apply the inequality. The case when G partial is a degree d-2 monomial is already a very famous case. This is how you get the Alexander-Fenchel inequality for mixed volumes. Here's another combinatorial application of algebraic matrix. So there is a topic in matroid theory called the matroid union. And here's a statement, theorem definition due to Nash-Williams. So he formulated this to unify several known statements in graph theory. The theorem is that if you have two matroids M1 and M2, and if you take all possible unions of independent sets from one and the other, then the resulting collection is again a matroid. That's the theorem. And the definition is that the resulting matroid is called the union of M1 and M2. And the intersection of M1 and M2 is defined using matroid duality, can equally be described using the intersections of spanning sets of M1 and M2. So in the 70s, Welsh, almost immediately after Nash-Williams' work on this matroid union, Welsh proved by direct methods that if M1 and M2 are algebraic matroids over K, then their union is also algebraic over K. In retrospect, this corresponds to that easy corollary, which says that if you have two realizable volume polynomials, then the product of the realizable volume polynomial is also a realizable volume polynomial. Because taking the product is almost like taking the union of all monomials in the sport. But the corresponding statement on the matroid intersection has not been known because of this open problem, whether the dual of algebraic matroids is algebraic or not. And one application of ours is that the dual statement is also true. If M1 and M2 are algebraic over K, then their intersection is also algebraic over K. And this is basically, modulo minor details, the other corollary saying that the product of realizable covolume polynomials is a realizable covolume polynomial. So let me now try to tell you at least the essential part of the proofs of all these statements. So the idea that almost always works is that covolume polynomials are like cohomology classes in product of projective spaces, and volume polynomials are like homology classes inside product of projective spaces. And the statement that you have a covolume polynomial and act on a volume polynomial, and the output will be a realizable volume polynomial, amounts to eventually the statement like the following. Suppose you have an irreducible subvariety inside the product of projective space, and suppose you have another irreducible subvariety in the product of projective space. Maybe you're allowed to take a generic translate of one of them and take the intersection. And can you show that the intersection is irreducible or not? And sometimes people think that the answer is yes. They misquote some version of Kleiman's-Bertini theorem, but there is no irreducibility part in those statements. So what happens is that the following lemma is actually null. Suppose you have a complete homogeneous variety X and some algebraic group G acts on it, and suppose you have two closed subvarieties of X, Y, and Z. So if X is something like Pn, it just so happens that the intersection of generic translates of two irreducible subvarieties happens to be irreducible so long as the dimension of the intersection is positive. But if your X is something like Grassmannian, then the same statement is not true. You can have two subvarieties, translate them in any way you want, but still the intersection will be reducible as many components. But the statement of the lemma is that the intersection of subvariety Z and the generic translate of the subvariety Y, it may have many irreducible components, but all those irreducible components will be algebraically equivalent to each other. And this is what saves all the polynomial statements. And if you want, you can formulate this lemma in the style of Kleiman, not just for subvarieties, but arbitrary proper map from Y and Z into the X. And then the statement is that the fiber product of these two morphisms living inside the usual product of Y cross Z may have like several reducible components, but they are all algebraically equivalent in Y cross Z and hence in X. And unlike Kleiman's situation, this statement is pretty general. So it applies basically in any situation where you have to be careful if you want to apply Kleiman's Bertini theorem, for example, in characteristic P. So for example, if you have two subvarieties, Y and Z inside P1 cross P3 of dimensions 2 and 3, so codimension 1 and codimension 2, where Y is defined by setting the first coordinate x0 equals 0, and Z is the image of the embedding, where you do the Segre of the second and the third P1, and push forward that particular hypersurface x0 and y0 2p plus x1, y1 2p equals 0. And then you notice that the intersection of generic translates of Y and Z is the disjoint union of two P1, where each P1 appears with multiplicity P. And these two P1s are algebraically equivalent to each other in the ambient variety.
So that's the main part of the proof.
So I'm going to finish part by a definition that I like, because I think it poses many very interesting problems. So the definition would go as follows. Suppose you have a collection of semi-positive 1-1 classes, W1 up to Wn, on a d-dimensional compact Keller manifold. So your semi-positive means that it's represented by a non-negative 1-1 form everywhere. And then you produce this volume polynomial in this analytic setting. You take a non-negative linear combination with coefficient xi of these 1-1 forms Wi and produce a polynomial, and it's equally easy using the Algebraic relations to show that the resulting polynomial is a Lorentzian polynomial. And in particular, its support must be a polymatroid. So this defines the class of realizable analytic volume polynomials, simply these polynomials and all their multiples, and therefore realizable analytic co-volume polynomials, simply these polynomials where you invert, take the reciprocals of all these monomials, and therefore also analytic volume polynomials, which are limits of realizable analytic volume polynomials, and also same for analytic co-volume polynomials. So 4 classes of polynomials. The first question is whether the main theorem that shows the duality between volume polynomials and co-volume polynomials is still true in this setup. Because the proof is very, very algebraic. And it says almost, I think, nothing about whether the answer of this should be yes or no. Okay, if you like the bonus problem for your calculus student from yesterday, I have one more. This is a little bit maybe more difficult because yeah, but it's different in the sense that it's not a multivariable problem, because this problem is already interesting for one variable functions. So maybe it's a bonus question for your real analysis students. So here it goes. So let's forget everything about volume, co-volume, anything like this. Let's just think about this duality between volume or whatever polynomials and co of those class. And maybe I'm just working with the homogeneous polynomials in 2 variables, just for simplicity. Can you give me a class of polynomials so that if I produce a dual of that class simply by taking complements of monomials, then these pairs satisfy the duality statement in the sense that co-class is exactly the class of polynomial differential operators that preserves the original case, and vice versa. We have seen examples: Lorentzian polynomials, volume polynomials over K, one for each K, but maybe they are all identical. And one more, and to maybe less of to avoid trivial examples, let's say that our class of polynomial is preserved under non-negative linear change of coordinates, like all our examples. And then I can only think of one other trivial example, which is the set of all non-negative polynomials. The dual will be the set of all non-negative polynomials. But other than that, can you construct by hand a class of polynomials which satisfy this duality? So this is a fun problem. And maybe the class of analytic volume polynomial will give you a new class. Another question that I find very interesting is the following, perhaps very overly optimistic question. Is every matroid the support of an analytic volume polynomial? So for many, many years, going back to Hilbert, people have been obsessive about finding the right axioms for combinatorial incidence geometry. They wanted to define the projective space, for example, by purely incidence axioms. And now we know that it can be viewed as a particular kind of matroid axioms. And then they were puzzled by the fact that if you place the reasonable axioms, then they see strange projective planes, for example. So there's projective planes of order 9, you can construct it using P2 over F9, but then there are two others that does not come from any finite fields, unless they are just weird and don't seem to have any properties. So they were always worried about the possibility that maybe they are missing an axiom that will rule out the things. And then there was this long search for this missing axiom of matrix theory or incidence geometry. And then there are various results that says that you can probably not find the missing axiom, or there is a missing axiom. And one crazy possibility is that maybe this is just because everything is really analysis. So maybe it's just the case that every matroid or polymatroid is the support of an analytic Boolean polynomial, and this was what matroids are in the first place, and you don't have to really worry about whether something is realizable in this sense or not. But in any case, I think the tantalizing lack of tools to answer questions like this, I don't know much analysis, but I think this is interesting directions for future investigation. I'll stop here. Thank you.